I have the pleasure of introducing our speaker, Eli Wiston. And so Eli Wiston is a fourth-year PhD candidate in the astronomy department at UC Berkeley, where he uses radio observations to uncover unique properties of explosive events outside of our galaxy, with focus on unusual supernovae. He loves sharing the wonders of the cosmos with the community through work with community resources for science, sharing demos at science festivals, and organizing Astronomy on Tap. Another great opportunity to see very astronaut-like talks. So please follow their Instagram page. And outside of science, Eli enjoys baking, playing Dungeons and Dragons, and dancing the Lindy Hop. So please, Eli, take it away.
Thank you, Daniel, and thank you all for coming out here tonight. We're going to start our story tonight in the year 1054 AD. Here, Chinese astronomers were observing the night sky and recording their measurements every night, when one night they observed the emergence of what they called a guest star in the night sky. Now, we now know this to be the explosive end of a massive star's life, a supernova. Now, in the past 1,000 years, we have gotten a lot better at finding these guest stars in the night sky. We take pictures of the sky every few nights and look for differences and see the sudden emergence of supernova in our images. But fundamentally, most of these observations are still looking at the same properties of that light that those ancient astronomers were, the visible part of their electromagnetic spectrum. And there's a lot to be learned by looking at this visible light, but it is only a small sliver of the total electromagnetic spectrum. There is a wealth of information to be gained by looking at the other wavelengths, and tonight I'm going to share the wonders of our longest wavelengths, the radio waves. I'm Eli, and I'm going to be telling you about tuning in to stellar explosions, radio observations of supernovae. So a quick roadmap for what we're going to talk through today. I'm going to start with some introduction about what supernovae are and why we should care about them. Then I'm going to bring in the radio observations, show how they work and what they can tell us about these objects. And finally, I'll get into my own research, where I specialize on, as Daniel said, these unusual supernovae, the ones that are bright at late times. And I'll also say I love answering questions. Feel free to raise your hand at any time. If we get too bogged down in one area, I might move on, but otherwise, fire away. So we'll start with what is a supernova. And to understand this, we first have to start with what a massive star is like. A massive star is mostly this big collection of hot gas. And a big ball of mass, all it wants to do is collapse in on itself by the force of gravity. And the only reason this star isn't completely collapsing is because in its core, it's doing nuclear fusion. And so you can think of these massive stars as a constant battle between these two forces. You've got gravity trying to make the whole thing collapse, and then it's being resisted by this outward pressure from nuclear fusion. And it's millions and millions of years of this constant battle between the two forces. Now, to understand fusion in a little more detail, I have one graph that shows, on the x-axis, we're going to see the different elements in ascending order of weight. And on the y-axis, we have what we call the binding energy per nucleon. And this has some complicated nuclear physics, but the important way to read this plot is just to say, if we go from an element that is lower on the plot to a higher one, we get to release energy. And if we are going down the plot, we have to put energy in to make this reaction happen. So if we look at this side of the plot, we can see that the only way to release energy is to go to lower mass elements. This is the nuclear reactions you might be more familiar with. Nuclear fission. This is what powers our nuclear reactors here on Earth. Over here, we can instead get energy, and a lot more energy, by slamming elements together to make heavier ones. And this is our nuclear fusion. So you can see you can keep gaining energy until you reach around iron. And at that point, you can no longer produce energy through fusion. So in this core of a massive star, when we're undergoing fusion, we start with a big ball of hydrogen. And we're going to keep fusing heavier and heavier elements. So our core of hydrogen starts fusing into helium. So then we have a core of helium surrounded by hydrogen. Then that helium is going to fuse into carbon. We're going to have a core of carbon, then helium, then hydrogen. And it keeps growing with a heavier core and lighter elements going outwards. We call this the onion layer model of the star. And not every star will get all the way to iron fusion. You need to be pretty heavy to reach the temperatures that you need to make that happen. But the biggest stars that are greater than 8 times the mass of our sun are going to get all the way to iron fusion. Yeah.
Presumably you can't cut open a star like this, so how do you know that?
Yeah, that's a good question. Some of it is these nuclear reactions. We have them mapped out pretty well. And while they are fusing and the main product is these heavier elements, they're also giving off other signals. And those are able to escape from the core of the star. And then we see those to confirm our ideas.
What's the highest element in our sun?
Ooh. It might just be helium or carbon. I'm not sure. Yeah.
If fusion produces more energy than fission, then why do we do fission in our nuclear reactors? Probably because it's dangerous, but
It's partially it would be dangerous, but it's also because, as I talked about, some stars can't do fusion of these heavier elements because you need really high temperatures. And so even though the net result of the reaction is to get energy out, you are going to need to put a lot of energy in. And we just don't have those kinds of energies to do fusion here on Earth yet. I know people are working on what we call cold fusion, but that has not been cracked yet. And you will definitely hear about it in the news if it is. Okay, so we have this fusion all the way up to iron. What happens after that? Well, we've been waging this battle for millions and millions of years. But at this point, our core is iron. It has no place to go that will release energy. And so fusion gives out and gravity starts to win. And this is actually the start of our supernova process. Now, you might be wondering, I just seem to have described a really good way to get an implosion, a big contraction of the star. Supernovae are explosions. So how do we do that? If we start with our onion layer model of our star, we've just fused to iron, everything is stable, but now gravity is going to start to win. And here, the envelope and the core are both going to start contracting rapidly. Eventually, the core actually contracts to be so dense that it is unable to compress any further, and so it's going to be this stiff, solid object. Meanwhile, the rest of the star is still rushing towards it. And so you end up like a rubber ball bouncing off a concrete wall. You get this rebound effect. And all that material that was rushing in gets reflected back outwards. And that shock wave is going to travel outward further and further until it frees the bounds of the star, and we end up with our explosion. So why should we care about these? I imagine if that you are coming to this talk, you are already interested in these on their own merits, but I'll offer some selling points. The first is that supernovae are in the realm of the extremes of the universe. They are extreme amounts of mass, several times the mass of the sun. They are extreme amounts of energy, enough to eject all that mass out into space, extreme densities in the core of the star. It's a place where the grand scales of general relativity and the small scales of quantum mechanics all come and unite. These are conditions we could never hope to replicate in our labs on Earth, but we can observe them with our telescopes. And so I consider these the greatest laboratories in the universe, the extreme events out in space. They can touch on physics that we could never do on Earth. My next reason comes back to this quote. Does anyone know who I can attribute this to?
Carl Sagan.
Exactly. This is Carl Sagan. Said, the cosmos is within us. We are made of star stuff. And if we remember our onion layer of the star, he's exactly right. We have much of the key ingredients of life being fused in the core of these stars. We've got our carbon, our hydrogen, our oxygen. I'm going to make one small addendum to Carl Sagan's quote here. If we are all made of this star stuff, but if it was just locked up in stars, it would never come to be a part of us. And so we need something, maybe an explosion, to hurl all those elements across the universe. So I'll make my slight modification and add myself to this quote. All right. I'll pause here for questions. Yeah.
I just if there's elements beyond iron, but how do those get made? If they're not.
Yeah. So part of that is actually another point. Some of them are fused in these explosions. It's not energetically favorable to fuse things together, but you're hurling things at such high speeds that can happen anyway. I'll actually have a slide on this I'll bring up. This is one of my favorite plots in astronomy. This is the periodic table by origin. And so you can see all these different sources of making our heavy elements. A lot of them are made by these merging neutron stars, which if you've heard Daniel talk about his research, is all about these really heavy elements. And there's all these different mechanisms that can make these. Yeah. Yeah.
Maybe I'll answer this later, but how often do we have the opportunity to observe these supernovae? And also can we predict them ahead of time?
So we are finding them pretty rapidly now. It's a few, 3 or 4 every day. And thousands of them a year. Yeah. These are all happening outside of our galaxy. The rate that we have is roughly 1 per galaxy every 100 years. As for predicting them, we have some ideas of when stars start to get more turbulent. Maybe they're close to exploding. If you've heard about Betelgeuse, that's the star nearby, not nearby enough to cause any damage, but nearby to be really exciting for astronomers, that we think might be showing these signs, but it's saying it's going to explode soon, either tomorrow or in the next 100,000 years. So, yeah. Still figuring it out. Yeah.
So these things are popping off sort of over, we've got about 13 or 14 billion years to consider here. I presume that's maybe you need to have stars formed before they can start popping off, and then they have to pass through a certain amount of their lifetime. You probably have galaxies formed before that even happened. And then they pop off, and this stuff then has to diffuse through their galaxy, probably, and then coalesce enough to, make steel case desks and things like that.
Yeah.
It just seems kind of funny that this gets blown out at this really seemingly low density, and then son of a gun, here we are. With enough of these high mass, these metallic things, nuclei, heavier than helium, to do all sorts of interesting things with.
Yeah. So there's 2 explanations here. I think the first is that while these things take a long time, we've been kicking it for 13.8 billion years, so we've had some time to get there. But also, these supernovae with these very massive stars, the most massive stars burn the brightest and also die the quickest. And so it doesn't take as long as the lifetime of these smaller stars to reach this explosion point.
Of course, in the early universe, you have more heavier stars, more very massive stars. And like you were saying, they have short lives and they explode, and here we are from their cast-off elements. But my question is, what causes white dwarfs to explode?
So that is actually the type of supernova that I'm not going to be talking about today. I do core collapse supernovae, but this is called a thermonuclear supernova.
Type 1A?
Exactly. Yeah, so these exploding white dwarfs occur from these compact objects accreting mass from a companion star. It gets too massive, and that initiates an explosion. And we don't know the exact mechanism behind that. They're still trying to figure that out. I'll do one more and then jump back.
Very quickly, what are the other ways a star dies, and what percentage of stars die in supernova?
So the other main way that stars die, we call it like not with a bang, but with a whimper, where it'll expand outwards a lot and become a red supergiant and just kind of lose grasp of its outer layers and leave behind this white dwarf. And that is the vast majority of stars are going to do that. The way stellar masses are distributed, most of them are very light, and it gets less and less common to find one that's heavier. All right, I'm going to jump back to radio astronomy. So, hopefully sold you on supernovae in general. Let's talk about why we should use radio telescopes. And my first reason here is going to be very practical. This image I'm going to show you looks at, as a function of wavelength, the atmospheric opacity to different kinds of light. It's essentially, for different kinds of light, how much is going to be absorbed before it reaches the ground. If we start with our really high energy kinds of light, our gamma rays, X-rays, ultraviolet, almost all of that gets absorbed by the atmosphere before it reaches the ground. This means we have to send things into space, but we are very lucky for this. High energy light is not something that you want to reach us, so we are very grateful to the atmosphere for that. If we move on to our visible light, we also call it optical light, we kind of use them interchangeably. This is looking a lot better. We're still going to suffer some atmospheric distortion effects, but overall you can do a lot of good astronomy from the ground, and that's why optical astronomy is so popular. If we look at our infrared, we are looking a lot worse again. You can peek through a little bit of it, but this is part of why the James Webb Space Telescope is so exciting. It's really good at looking in the infrared, and it's rising above all this atmospheric disturbance. And then, when we get to radio, we have a beautiful open sky. Look at, nothing's getting absorbed by the atmosphere except for these really long wavelengths that we don't really do our astronomy at. And so I would argue that if all this light is already reaching the ground, we should be making use of it. And so that's my practical pitch for radio astronomy. Now, I will invite in some of the practical caveats to this. Radio astronomy is quite difficult, and this is going to be the one equation that I show you today. This is called the Rayleigh criterion formula, and it shows why radio astronomy is so difficult. It is showing theta, which is the minimum angular separation between two objects that a telescope can resolve. So if you have a low theta, that's good. These two different blobs are separable. We can look at them and see that they're two different objects. If we have a high theta, these start to blend together and look like one big smudge on the sky. Now this is really important for our supernova science, because our supernova are not happening in random places in space. They're happening in galaxies. And if we want to be able to separate the supernova out from the rest of the stars in the galaxy and not have it just be one big smudge, we need enough resolution to separate these two objects. So that brings me to the problem. If we look at the right-hand side of this formula, we have the wavelength of our light, which, as I was emphasizing, radio is at our largest wavelengths. We are going to end up in this really high theta scenario. And the only way to combat that is with this denominator, the aperture diameter. That is the size of our telescope. It means we have to make our telescope really, really big in order to get the resolution that we want. To put it in perspective, the Hubble Space Telescope, which is a great telescope that can observe mostly in the optical, we have our 1 micrometer wavelength. With a diameter of 2.4 meters, we can get this angular resolution, which is very good at separating supernovae from their hosts. If we wanted to get that same resolution at radio wavelengths, we would need a 2-kilometer diameter dish. I don't know if this is possible from an engineering perspective. I'm pretty sure it's not possible from a financial perspective. But luckily, astronomers are very clever, and they have a cool workaround for this. And that workaround is telescope arrays. So our instrumentalist said, well, instead of having one gigantic dish that we can't really build, what if we have a bunch of little dishes in a field together? Each of these dishes has a small dish diameter. I say small-ish because it's still like 10 meters. They're pretty impressive. But together, they have a really large effective diameter. And that resolution is set by the maximum distance between two of these dishes in our array. And so this brings us into radio interferometry. It's a really cool process. We're basically having the signal arrive to each antenna at different times because of the very slight difference in position between them. But by measuring things really fast and doing a lot of complicated math with the time delays, we can use this to translate it into positional information about the target. It's kind of like how our eyes give us depth perception. So this is how we measure stuff in radio. But what are we actually measuring when we look at supernovae? To bring us back to this fun little GIF. If we break down the anatomy of this explosion, there's a lot of cool features to look at. In the middle here is the hot, dense material towards the center of the explosion. And this is what our visible light is really good at characterizing. But it is really limited to looking at these hot, denser regions. Radio, on the other hand, is really good at looking at the fastest moving material. And so it's probing these outer regions of the explosion. And so I may have been talking some smack on visible observing, but I actually think these two are super complementary, and you get a full picture of the object if you look at multiple wavelengths. So how are we actually getting emission in the radio from these fast-moving material? It comes down to shock interaction. We have all of this material blasting off into its surroundings. This creates a shock wave that is really good at accelerating the surrounding material. In particular, it really accelerates the lighter material, the electrons. This starts them moving really quickly. Fast-moving charged particles are going to produce magnetic fields. And then once you have fast-moving charged particles in a magnetic field, they are going to be manipulated by those fields. And we have what we call helical motion here, where the particle is going to start winding in this circle. And when a charged particle is moving quickly and changing direction, it ends up giving off light. In this case, when it's following this helical pattern, this is called synchrotron radiation. And it happens to be most prominent in our radio frequencies. And so we're able to pick up this interaction. Now, one question you might have, I just talked a lot about this hinging on interaction with the surroundings, but astronomers love to emphasize how empty space is. And sure, we have the star here, but what is it interacting with in its surroundings? And the answer is that these massive stars start getting really unstable in their last 100,000 years of life. And so they will start shedding some of their outer mass. We get this stream of mass loss. And now we've built up a surrounding environment for the star that the shock can then collide with and interact with. Now, the really cool thing here, once we get our explosion, this shock wave travels much faster than this mass was lost in the first place. And so the stuff that was lost days before the explosion, we get to sample in a matter of hours. For a year, we're sampling it in a matter of weeks. 1,000 years, we get to it within a year. And hundreds of thousand years, if we stare at it for many years, we can look back at that interaction. And so in this way, radio astronomy sort of acts like a time machine to the history of the star before it died. We often call ourselves stellar morticians, because we're looking at the cause of death and what was happening to it shortly before it died. Yeah.
So, just wondering about the radius of these, the particulates expansion and then the shock wave outward.
Yeah.
What goes on there? What if there's a poor little planet revolving around a poor little normal star?
Yeah, I'd say I don't think.
Will planets survive that?
I think a planet would probably be okay with the mass loss. I think once the shockwave comes through, you're going to want to evacuate.
Somewhere else.
Yeah.
Faster than it is.
Yeah. Yeah. Any other questions?
when you're looking with whatever devices you look to see supernovas, how long do you have to look at it before it goes away from your ability to visualize it? I know you're saying like different layers, you can have years, but I was wondering like, is it a blink and you miss it type of situation, or like will you be able to visualize it on the telescopes for like days or years after?
Yeah, that's a great question. Some of this I'm going to answer very shortly.
Amazing.
But in part, it does depend on the wavelength of light you're looking at and the sensitivity of your telescope. One of the cool things about radio is also that it tends to persist longer than our visible light. And so we can do this analysis looking back in time. All right. Oop. Then I can get into my work on radio supernova, starting with what these actually look like in practice. So I thought I'd show one of my radio images. This is a cleaned and calibrated field, and if we zoom in, we can see our supernova. Now, this is not telling us a whole lot of information. While it looks like you're getting some shape here, this is actually just the beam of the telescope. This is what an unresolved point of light looks like. We've gotten enough resolution to separate it from all the other objects, but not enough to really see any structure to it. But we are getting the brightness. So we get this 1 point of brightness. I think the projector died.
It overheated.
Can you
Okay.
use the TV over there above you while if you do the backup plan?
We'll see if it starts back up. In the meantime, any questions on what I've talked about so far? Yeah.
Well, I know you studied supernovae in other galaxies, but a lot of research has been done on the Crab Nebula. That's what you were referring to with the Chinese astronomers at 1054 AD. So what do we know about the Crab Nebula from radio astronomy?
Okay, this is actually something I will touch on towards the end of the talk, so I might defer that.
Okay.
Other questions? Yeah.
What are the sources of interference? Like you're picking up these radio waves. Are there other sources they have to filter out?
Yeah, so we, as radio astronomers, we have to deal with interference a lot. We call it radio frequency interference. Thank you, Daniel. Yeah, and it's all the sources you would think of. It's our Wi-Fi, our conventional radios, our TVs. And so radio telescopes, we like to get as far away from civilization as possible to observe with them, but we still have to do a lot of calibration. Luckily, we've learned how to characterize these signals pretty well, so that helps us filter them out, but it is definitely a pain. Okay, so I was saying, this is our image of the telescope. Through the telescope, we're not actually getting much shape information, but we are getting the brightness. So this is really just giving us one data point. But if we look at this at a bunch of different frequencies, and over time, we can develop a richer understanding of these objects. So I'm going to show our expectation based on our modeling in the physics of what this should look like. I'm going to show a light curve, which is a very common type of graph we show in astronomy. On the y-axis is just a measure of brightness, and on the x-axis is time. And our expectation is that these will rise over the course of a few months, reach a peak within a year, and then start to gently fade away. If we look how this pans out in practice, it's actually pretty close to the expectation. Data is always a little messier, but we are mostly seeing that rise and that fall in our population of well-studied radio supernovae. So this is a very satisfying result. Everything's matching our expectations. But there's one thing that was still bugging us about this, and it's that this whole part of the graph is not filled in at all. These were starting to fade away, so people stopped following them up, but it leaves this whole region unexplored. And it was pretty much unexplored for many, many years until only a few years ago when we had the VLA Sky Survey. The VLA is one of our best radio telescopes, and it conducted a survey of every patch of the sky it could observe, which is all the orange and yellow in this figure here. So most of the sky, just a little bit that was below the horizon they couldn't get. And so this gave us an unbiased study of the entire sky And so maybe there are some supernova lurking in there. Now, it would be impossible to look at every inch of the sky and do a search for these supernovae. But luckily, we have a great catalog of these objects. We have our optical astronomers that are discovering a few of these every day. And so our team went in and looked at 60,000 plus known optical supernovae and cross-checked their positions in the VLA Sky Survey. And for a few select objects in this sample, we found really bright radio emission decades after these explosions first went off. Now, I'll clarify that for the vast majority of these objects, we didn't find anything. But for 20 special objects, we had this bright light coming from them. And so with these observations, this plot is looking a lot more populated. We're filling in this late time part of the story. And we can see that these are standing out a lot from the trend that we expected. They seem to be getting brighter late in their lives. And so this plot sort of summarizes the entire goal of my thesis is to look at these objects and try to figure out what is happening, what is powering this late time emission. Now, to go through every object in the sample would take far too long, so I'm going to focus on one object that is especially interesting. It was so interesting that I just submitted a paper for publication on it. It's called Supernova 2012 AU. We nicknamed it the Golden Supernova because of AU on the periodic table. So I'm going to do a deep dive into our analysis of this object. Before I get into that, I'll pause for any more questions. Yeah.
What is relativistic? Relativistic VLAS.
So VLAS is just the survey that we used. So that was our shorthand for all the sources that were discovered through that. And then we were highlighting the relativistic ones, which are the ones that we inferred really fast shock velocities from, that are not at the speed of light, but more comparable to the speed of light. Yeah.
Why were you only able to find 20?
We think that, well, first, the VLA Sky Survey was great at its coverage, but it didn't get that sensitive. And so we're only seeing the ones that are really bright at these times. But we also just think that these are a bit rare.
Does that also sort of explain why, or not maybe doesn't explain, but is that one possible explanation for why the luminosity is higher than this other plots that you're showing?
It could be an explanation. It's part of, we are biased towards brighter things because of the survey, and also whatever is doing the rebrightening might be a more luminous source. Yeah.
Is there any spectral variation that you can see in the bandwidth that you're looking at?
So all of these points are at the same frequency because VLAS did everything at about 3 gigahertz. But what a lot of our follow-up of these sources is looking across a bunch of frequencies to try to get a more complete picture of the story.
I was just wondering if you're able to complete any part of the graph for these new points that you picked up, these orange ones. Like, it looks like you just got one sample and you don't have a graph yet.
Yeah, that is a great idea. This was a plot that we made right after we got this initial sample, so it's just the points from the survey, but we have been doing follow-up, and so it would be cool to fill in this graph. We do have the data for that.
How long was the VLA survey?
I think it was a bit less than a year. Yeah.
Why can't you search every inch of the night sky? Like, presumably, from a naive understanding, it's like a finite search. So,
Yeah.
is it like the size of the data, or like the time intensity, or what?
It's more so that if we saw a bright thing when you were searching randomly in the sky, you wouldn't have a good idea that it's a supernova versus a bright star or another explosive event. So it's only because it's at the exact position of a known supernova that we can be confident. And if we were doing surveys more frequently, then we could do the game that optical astronomers do, where they do before and after pictures to look for emerging things. But these take much longer than that. All right, so 2012 AU. I will start with a more complete light curve here. This is our early time data for 2012 AU. Has this is in part an artifact of how I arrange the data, but we get a quick rise and then our fall over a time scale of about 6 months. People did analysis of this object. After these first 6 months, it looked very normal, and so we stopped following it up as it faded away. But then it was revisited 6 years later, and we get this remarkable rebrightening effect. And this is one of those where the luminosity in some of these bands is exceeding what it had at early times. So we don't have a great sense of what is powering this just by looking at this graph, but we can use our understanding of synchrotron radiation and the measurements at different frequencies to start to define some of the qualities that this emission has to possess. And so we have a little checklist here. We know that this is coming from a very dense region with a lot of electrons. We know that that region has to be pretty small. We know that it has to be expanding fairly slowly over these different time steps. We're going to need some explanation for our emission at early times and some explanation for this rebrightening. And crucially, the explanation for the rebrightening can't be something that was happening at early times that can also be observed. It can't be contaminating our signal in those first 6 months. So we explored a few different explanations for this. The first is to look at our conventional model of a shock interacting with the surroundings. And so the first possible arrangement of surroundings we considered was this torus model, essentially a big donut stretched around the star. And we're not just pulling this out of nowhere, we have actually observed this structure in nearby supernovae. And so if we look at our checklist, this torus is going to be much more dense than the rest of the surroundings. And it's also, because of that density, it's going to slow the material dramatically. That's going to help with our slow expansion speed and also keep it to a small radius. Our early emission is going to come out of the holes of the donut. It's going to interact with the less dense medium. And our rebrightening is going to come from interaction with the denser environment. Now, part of the reason that we aren't seeing this at early times is that it hasn't reached the donut yet. But even if it does, it is so dense that it is going to absorb the light at early times. And it needs to travel sufficiently through that torus to start having the light come through and reach us. So this looks like it's meeting our criteria at first glance, but we have to do our rigorous modeling, see if there is a precise arrangement of parameters that meets this description. We find a model that does fit the data fairly well, but the problem is this torus has to be about 10 times the mass of the sun, which is not really possible. And so we're forced to rule out our donut hypothesis. We next turned to this idea of a disconnected clump of material. Essentially, our idea was the problem with our torus model is that we needed so much mass because we needed to really slow this rapidly. But instead of slowing it down, what if we just have the shock proceed normally and then encounter something later on in its duration? And so this clump will be intrinsically small and dense. The shock will have decelerated a bit by the time it reaches it and slow down more by the time it interacts with this dense clump. The early emission happens normally with the interaction with all of the intervening material that is less dense, and then we get a rebrightening as it hits this dense clump. So this again seems like a promising idea on paper, but when we tried our modeling, we could not find any configuration of clumps that matched the data adequately. And so we were forced to rule this one out as well. Now, this is basically all we had for these conventional shock interaction models. And so our next idea, we had to go back to something that I kind of brushed past in my explanation of these supernovae. I was very focused on how we get this shock, but here we have something that was left behind, the dense core that everything bounced off of. And this dense core is what we call a neutron star. These are super cool objects. They are the densest things in the universe aside from a black hole, and it is stuffing about the mass of a sun into an area the size of San Francisco. So extremely, extremely dense. And what happens is all stars have some intrinsic rotation to them. The sun is rotating, and it's doing it pretty slowly. But during collapse, you are getting this very sudden contraction of all of your mass. And so it's a lot like a figure skater tucking their arms in. You're going to get a rapid acceleration, and the rotation is going to be much, much quicker. So much so that at the most extreme, these objects can be rotating, making a full revolution every millisecond. We call these objects pulsars. They are rapidly rotating neutron stars. And because we're moving all these charged particles around so quickly, we're producing these really strong magnetic fields and this stream of charged particles coming off of them. This really fast rotating energetic thing looks like a great powering source for our rebrightening event. And we call this kind of event a pulsar wind nebula. Out here is the fastest moving material coming off of the star. That's what we normally are sampling with our radio. But here instead, we have this inner object interacting with the slowest moving material. And this is producing bright radio emission. Now, we have seen objects like this, but they're all inside our galaxy and much older than this object. Now, if we go through our checklist, we're going to be pretty small because we're interacting with the innermost region now. That inner region is also the densest, and it's the slowest moving. Our early emission is coming from that same fast-moving shock that it normally is, and our late emission is coming from this pulsar wind nebula. And similar to the torus, the reason we're not seeing this in our early time data is because there's all of this material that the light has to pass through on its way to us, and it all gets absorbed until the explosion has carried out enough of the material, diluted the field enough that we can see through to the center. And when we compare this to our models and look at the data, this is looking like a pretty promising model for our mission. This brings me back to the Crab Nebula. If you look up in our lobby, this is plastered on the ceiling. And this is our best observed pulsar wind nebula. And this is part of the reason we could be so confident in our final conclusion that this looked like the best model. We could make a lot of comparisons to this pulsar wind nebula. It's the best observed one, and it is the one that we know the exact age of because of our friends in China 1,000 years ago making these records. So that brings me to the end of what I've prepared today. I'll go through some summary points and then open up for more questions. Supernovae are these really exciting objects. They're the explosive ends of stars, and they provide a laboratory for these really extreme physics and the seeds of life throughout the universe. Our radio telescopes let us measure the interaction between the fastest exploding material and its surroundings, or sometimes a pulsar and the innermost surroundings. These late-time observations that I work on show these really fascinating rebrightening events that can point to really interesting new physics. And we looked at one example, the golden supernova, that has become our best candidate for an extragalactic young pulsar wind nebula. I'll finish off here and take any remaining questions.